Today I will be trying to convey you some latest ideas on the issue of a particular problem in ocean sciences, of course, which is related to my own field, but I'll try to be general, and I'll try to convey the information as accessible as possible. As we've seen in the polls, we have a quite diverse audience, students to professors from different institutes in Turkey as well as across Europe. And again, thank you all for joining. So I'll try to be as accessible as I can. As Barish said, please enter your comments in the chat room at the end. After about 45 minutes, we will try to address them as much as possible, including your questions. So actually, before starting our discussion, Happy Earth Day. This is the 50th, I think, anniversary of the Earth Day, International Earth Day. So that's the Earth, our blue planet. It's called the Earth, but as you all know very well, most of you are marine scientists, it is a truly blue planet. And of course, the question, the central question that we are all working on to some extent, or we are related to, is how much do we know about the blue? The blue covers about 2/3 of the planet, but it is not maybe attracted as much as funding as the space program, such as the Apollo mission, which took this photo of the blue planet. So that's partially why we are trying to also raise awareness to attract more attention to ocean science, especially in these times of global level crisis, such as the COVID pandemic or the climate crisis. But today's topic is, of course, the blue planet is a huge topic, and in this virtual room there are many world experts on physics of the oceans, chemistry, biology, and many of them also, hopefully, we will be giving webinars sharing their ideas in the following months. But in this particular talk, we will focus on the deep sea, the deep blue part, let's say. And here you see the deeper areas of the world's oceans in more blue form. Of course, blue indicates deeper areas, and light blue indicates more shallow areas. As you can see, we have, of course, around the continents, light blue seas. They are shallow continental shelves or coastal regional seas. But also in the middle of the open ocean, I hope you can see my mouse, the tip of my mouse. We also have kind of shallower areas in the middle of the oceans, which correspond to mid-ocean regions that we will be also discussing today. So actually, before the Second World War, even before 50s, middle 50s, 1950s, this is speaking of the 20th century, we didn't know much about the blue, especially the deep blue, we even knew nothing about. So this map is a little bit historical, but it's more like artist rendition of the mid-ocean regions, the underwater mountain chains, and the trenches, which are shown in dark color here. You see, so this map in a way changed the world. Actually, it resulted in a revolution, maybe the last scientific revolution that the world witnessed after the revolutions by Newtonian physics or the Einstein's relativity theory. Another important revolution in physical sciences, of course, happened in geology, the plate tectonic revolution, which the idea, at least in different versions, were put by different people. Alfred Wegener is one of them, of course. Today we have a couple of listeners from the German Alfred Wegener Institute. So it's named after the scientist who first proposed the continental drift idea in the earlier decades of the 20th century. But it took about 50 to 60 years for those ideas to be tested, especially the generation of new data from the ocean floor, the soundings that you see here became very important. And the person you see here, the scientist you see here, is Marie Tarp. She is a female, one of the first female oceanographers who couldn't go to sea due to conditions of her age, but she analyzed this vast amount of data resulting from ocean soundings from all over the world. These are basically bathymetric data collected perhaps during the Second World War and after, primarily by big American institutes such as Lamont or Scripps or Yucel. So she was analyzing and converting all these data to the map that you see here, actually. Of course, the map was later stylized and by different artists. Here you see a version by Beran, produced in 1977. But this map was pretty much changed how the scientists viewed how the Earth functioned. Because especially with this map, with, of course, the additional different types of data, the idea that the Earth's crust consists of different plates, actually, either colliding with each other or becoming spreading away from each other, this became relatively very apparent. So people actually then started believing what they saw, including the vast majority of the scientists, and that's how the plate tectonic revolution happened. So that's one of the things that as we will discuss in the very end, that controls evolution on our planet, as well as carbon cycle and ocean biology. So Murray Tarp's map, as I said, indicated the presence of mid-ocean ridges, which you see here and here. And here I'm going to show you a photo from the mid-ocean ridge near offshore Mexico or Costa Rica. So this is part of ridge where I had a chance to dive several times with research submarines. So looking out from your porthole in a research submarine, this is how it looks like when you land on the seafloor around those mid-ocean ridges. Actually, it's glassy basalt, nothing else, not much sediment, because simply not enough time passed for sedimentation to pile up and produce sediment columns. So it's basically you land on a kind of a different planet made up of glass and dark basalt. Glass in geology, this is basalt. Basically magma here erupting from the subsurface, cooling very fast and producing these sort of shiny rocks. Actually, if you go to Çatalhöyük near Konya, you will learn that they also used to base their economy in the Neolithic times based on these sort of volcanic glass, which is called obsidian as well. Anyhow, in the mid-ocean ridges, of course, you find these sort of rocks. But this was not exactly, at least for my work, for our research, we did not go there for the study of these rocks. There are very, very good people who are working on these rocks as well. But we were particularly interested in finding volcanic emissions like this. So around these mid-ocean ridges, a vast amount of volcanism occurs. The continents, especially in this type of ridge, they are spreading apart from each other. So new crust, actually new ocean crust is being formed. And along the very central axis of these areas, you find these huge structures. We call them hydrothermal chimneys or hydrothermal black smokers, if they emit black smoke. If you look carefully on the left, we have a nice smoke coming up. So typically they are really very complex, tall, big structures, and a lot of different types of fluids at different rates they come out of these structures. And they bring, for the purpose of our talk, of course, they bring a lot of metals, dissolved metals, to the oceans, among many other things. Their primary influence is that they bring these metals. The revolution that I spoke of basically gave us how the ocean floor looked like. We understood in the late 50s and 60s that the ocean floor was not just a simply, flat place. It consists of mountains, mountain ranges, deep trenches. But at the moment we are on the verge of, I would say, another revolution, because now we have a new and very, very different types of data emerging from the ocean itself, from the water column itself. Here you see dissolved iron concentrations measured by the GeoTraces program, international really state-of-the-art program on trace elements and their isotopes. And here you can see the the chimneys, actually, the fluxes of metals from those really focused areas, they result in huge changes in ocean chemistry, which can be seen in this graph. So we will be talking about this today. You see iron especially can be emitted from mid-ocean ridges, but we will also briefly talk about this other source areas, red meaning that there's an iron source, so iron is coming. So in this case, parts of the continental shelves, apparently they're also a big source of metals. So briefly, I'm sure many of you are already familiar with why metals are so vital for life, but for those of you who are not familiar with the subject, metals, especially transition metals, the ones that are called transition metals, such as iron, manganese, cobalt, nickel, vanadium, they like to exist in different oxidation states, which meaning that they like to give and take electrons from their outer orbit. In a way, they are like a very, very versatile football player. They like passing, they like giving and taking. And for this versatility of electron transfer, they are actually, as a result of biological evolution, they were incorporated into many enzymes and also non-enzyme proteins. Here you see many of some examples about these proteins. So metal-containing proteins, they are called metal proteins. And especially enzymes, they cannot function without these sort of redox metals, basically. Any life function is based on metals, from oxygenase to nitrogenases, phosphatase. So pretty much all life functions in all domains of life are based on metal catalysis, metal redox reactions, which are happening in enzymes and proteins, of course. So as a result, metal availability control life. Here's an example of how in your blood, your red blood cells, hemoglobin, can carry iron, can carry oxygen. So this protein includes iron, iron 2 and iron 3. So when it's iron 2, when it's reduced form, it can go and stick to oxygen and carry it to the cells. And then it can release it whenever it's necessary, being back to this iron 3, iron 2 transition. Okay, so basically different iron and other metals enter to oceans from different sources. I'd like to ask Pinar here to activate our new poll, if possible. Yes. So so far we have really realized about 4 or 5 different big major sources of iron. So rivers, atmospheric dust, deep sea vents, shelf sediments, and you wouldn't believe it, even cosmic dust is a source of iron. So just wanted to have your impression about which one do you think is the most important according to you, based on your readings or views so far? Okay, answers are coming in. Looks like this audience is very much familiar with the vents. Another 10 people will vote. All right, I think we are there. So let's have the poll still open at the moment. So yeah, this audience apparently they are very familiar with vents. So of course this depends on which part of the ocean, which regional sea you're looking at. But here we are talking about a very, very general basis. Of course, the rivers is one of the biggest sources. Actually, the answer to this question is not easy. The real answer is we don't know. It's very hard to estimate these things, the magnitudes of fluxes in and out of oceans or any marine system. But in this case, the general opinion is that rivers, yes, they do, of course, bring a lot of particles with iron, but they don't really reach, they are trapped in the coastal zone very efficiently, and they sediment in the outer shelf. They become sedimented. So indirectly, actually, they translate into iron release from shelf sediments. So when you look at the numbers, the iron released from shelf sediments is one of the largest. Is the largest, maybe, to be honest. Dust is very, very important. So in a way, yes, continents influence ocean iron cycle and productivity, but mainly through dust, through atmospheric dust, and indirectly, of course, through shelf sediments, maybe after a certain time, but with dust, really. Because dust really directly lands on the phytoplankton habitat where it's needed. And deep sea vents, yes. Recently we have realized that very recent estimates equate deep sea vents to dust in terms of its immediate impact on the ocean productivity. Sediments actually are a little bit more important than you would think. Cosmic dust grains, actually just a month ago I heard that this was also a significant source, but nobody knows its reactivity, of course, and it may be very old iron, which wouldn't react with anything at all. Anyway, yeah, we can close our poll. Thank you very much for participating. And of course, at the moment, our understanding of iron cycle, this is the result of many, many different groups and people and a lot of different measurements. But especially, yes, vents and sediments, it's a big source of iron, but there are also processes, recycling and remineralization processes in the water column, the especially deep water circulation and interaction between the upper ocean and deeper ocean through, for example, mesoscale features, eddies, or small-scale physical features. Now we understand that they are also very, very important. So it's a very complex problem, including a close collaboration between marine chemists, physical oceanographers, biologists, which is actually why oceanography institutes like IMS or NEOS, we have participants from NEOS or Southampton, are constructed around multidisciplinary groups to be able to address these sort of problems. All right, so why do we care about this? Of course, one of the biggest questions of our times is the carbon cycle. Will the ocean be able to continue to absorb CO2? What's going to happen to the atmospheric CO2? Is it going to keep increasing, keep it the rate that it does today? And of course, an important thing to look at, to understand our future, our own climate future in the next few decades is to look back to the very recent past. In this case, you see atmospheric CO2 concentrations measured in, I think, Antarctic or Greenland ice cores. I have to look that up, but especially in the ice ages, when there were a lot of, it was much drier and colder, there were big ice caps, of course, and in those times, people found that atmospheric CO2 levels were very low, by like 150 to 160 ppm compared to the interglacials. And now the prevailing idea is that this excess CO2 was kept in the oceans. We don't know exactly where. Southern Ocean is a big candidate, but we don't know how really this CO2 was kept. There's this idea that productivity was high, and maybe you heard this hypothesis. John Martin has this famous iron hypothesis, where he suggested that during the ice ages, of course, dust deposition, atmospheric dust transport was higher, and this resulted in increased productivity. So it resulted in iron fertilization through dust, which is a great hypothesis, which led to a lot of new work. But at the moment, we also collaborate with many biogeochemical modelers around the world. This is a scientific committee of ocean research working group on iron model intercomparison. Basically, these are biogeochemical models used to predict Earth's climate. They are coupled to other physical models or different radiation models to predict the biogeochemistry of the oceans. And when you look at these models, of course, especially if you want to understand the ice age, the interglacial variability, the iron sources and things must be really addressed, because that's a big influence. So here you see, we've talked about dust, sorry, dust, sediment, hydrothermal, rivers. They don't yet include cosmic dust, but I know that my colleagues are also working on including cosmic dust. But you see, sediment is the biggest source. Different models, they use different assumptions, of course. Most models, they don't yet include hydrothermal fluxes. It's not because that the model couldn't, it's just it didn't come to that point yet, but it will. In some models also rivers are set to 0. But when you look at those models which include all sources, you see the sediments are really the biggest source, with dust and hydrothermal being comparable to each other. At the moment, but you see there are huge uncertainties in the estimates of different models, and the way that the models also work are different, partially because our lack of actual observations in the ocean, which I'm sure many of you are very familiar. This is hindering us from better predictions. So, in our group, we are trying to contribute to this question, especially from the viewpoint of how iron is being mobilized from the seafloor to help reduce the uncertainties with these sort of estimates. But as you'll see, we think especially the hydrothermal flux and sediment fluxes from continental shelf, they have a lot in common in terms of how redox properties of iron leads to some interesting chemistry, further leading to production of nanoparticles or different iron species, which then lead to this sort of fertilizing capacity. Before that, as a result, this sort of work is helping us to collaborate with many people on different questions, such as what controls ocean's long-term primary productivity. Very big question, of course, very difficult question. So what causes this glacial scale CO2 variation is a very pressing question. But you can even go further if you understand how this works. You can even go further back in time. How did metal availability in oceans control the life's evolution and diversification is also a very interesting and open question. And as I said, you need to invoke a lot of knowledge. You need to borrow a lot of things from chemistry, redox chemistry to different fields to be able to answer these questions. So let's look at the hydrothermal systems. Let's go back to again our dives with submarines, and let's look at in detail some mechanisms governing the metal mobility in these mid-ocean ridge type, at least black smoker systems. So these black smokers, they are actually they're like the textbook or the famous, let's say, image of hydrothermalism. They were only discovered, they were only first seen in 1979. So just about 42 years ago. So quite new observation. But here the idea is that, yes, it's the place where a lot of iron and other metals enter the oceans, but they don't really, they're only part of a bigger story. Here, at least, we will propose that they have a part, but there are other mechanisms governing fluxes from deep sea. For example, the subsea floor. This is the black smokers are only the tip of the iceberg. There's a whole reactive system beneath this. Hot seawater reacts with rocks. There are microbes probably also altering the composition of hydrothermal fluids that we have no idea about. Then a lot of things get lost in the subsea floor, such as magnesium, so sulfate. So for a lot of different ions, these hydrothermal systems are a sink, but for some other things, it's a source, such as iron. So there are these sort of processes. There are reactions near seafloor vents, and there are also the oceanographic water column, deep water processes, which I will now briefly try to cover. Factors affecting different subsurface geochemical reactions. It's a very complicated subject again, but very simply, the age of the system is very important in that regard. When the mid-ocean ridge formed, or the type of the ridge is also very important. The heat source, where is the magma? How far is it from the seafloor? The mechanical structures of the seafloor, fractures, fissures in the crust, composition of the basement rock, temperature, pressure, so the amount of water volume above it, magnetic interactions, vapor brine phase separation. So you see here, in order to understand a seemingly oceanographic or marine chemistry type problem, you need to understand a lot of geological processes. So this is an attempt we have done a few years ago about using available data. We looked at basically the effect of pressure, which is the water depth, the effect of spreading rate, so that's the speed at which plates are separating apart from each other. So we looked at those, and the data are so scarce, of course, but at least you can see some trend, for example, with increasing spreading rate. So the faster opening ridges kind of released more iron in this case. This was interesting because even these sort of simple relationships, they still don't exist in global models, but they can be used actually, quite simple relationships, if you can, of course, have a handle on them with large amount of data. So what generates these big, let's say, trends? Of course, it's we are talking about a very complex water rock reaction system. Beyond reactions, not only happen near the black smoke, that's the idea. So even down to 1 kilometer, you can have a lot of reactions, mineral formation reactions and water rock reactions going on, which then actually alter your seawater composition. It transforms it into a more focused high temperature. So the oxygen containing relatively cold seawater through all these reactions became very hot and reduced anoxic and metal-rich fluid. So for those of you who are familiar with the Black Sea, in a way, you have the surface Black Sea water goes in the seafloor, and then you have the deep water even coming out. So it's really like that in terms of the differentiation and redox and everything. That's the reason why there's so much life around that. We'll come to that as well. But an important process with respect to metals is the phase separation. This is basically boiling. Sometimes the hydrothermal fluid just boils beyond the seafloor, in the subseafloor, and when that happens, you have a lot of actually the chloride, the salts, they are left over. The vapor becomes more dominated in your output that you measure on the hydrothermal chimney. But so some systems are really dominated by this, some are not, some are more dominated by the more salty phase. And those phases contain actually more chloride, which is a, maybe you'll remember from one of my earlier slides, metals like to be coordinated. They exist in couples with more than one couple, and then chloride is a good couple. It can bind to iron and then carry it forward. So when you have these sort of things, now we are understanding that this can increase the metal variability. Another review we published last year, just updated these data sets. It's pretty much still, we think that the fast spreading mid-ocean ridges contain actually less iron, and slow spreading ridges, they tend to bring more iron to the ocean. There are, of course, other types of ridges, back arcs, such as in subduction zones, or sedimented mid-ocean ridges as well. So there are a whole diversity of seafloor ridges over there. Okay, another type of reaction is basically the things that are going on in this black smoke that you see, and they're also very important. So the first set of reactions, they mobilize the metals, but then it's really the question of how much metal actually you will inject to your deep sea, deep cold water volume is really determined by this scale. So here we are talking about reactions to millimeters to tens of meters scale. This is actually how we sampled those black smokers, by the way. These are very high temperature fluids, 300 to 400 degrees Celsius. So you need to sample them with not a classical Niskin bottle, of course, so you need to use titanium syringes, so-called. That's how you sample them and then bring them up on board. Of course, we will, for lower temperature fluids, we also use chemical sensors. I'll come to that in a minute. So a lot happens in these black smokes, but basically, the black smoke is particles, mainly iron sulfide particles. And lately, actually, it was assumed that all the rocks you see around this black smoke is basically iron sulfide and other things. So people assumed that any iron coming in was pretty much fast oxidized with the oxic seawater, and then everything became rocks or just the iron metallic deposits. By the way, these areas are very valuable in terms of mining, which is another issue. But so that was the thinking, but especially in the past decade, we've shown that these sort of fluxes are mainly carried through the nanoparticle phases, especially the black smoke near the source as well. So these are really natural occurring nanoparticles that are produced by the hydrothermal system and injected into the deep ocean. Nanoparticles, first of all, they are very small, they will not settle very fast, and they are much more resistant to oxidation, more importantly. So this, as you'll see in a moment, this explains a few ideas about how iron is traveling in the ocean itself. All right, so in addition to these, we do, of course, we try to reach out to mid-ocean regions and collect new samples. So here I'll briefly mention our recent cruise that happened in 2018 in collaboration with our French colleagues. And here one of our master's students at IMS had a chance to go and collect samples for his thesis, Serhat. You can see Serhat here, who actually prepared many of these slides here and ideas. So this was a really great opportunity because in the mid-Atlantic ridge system, we were able to reach out to many different vent types. Lost City was one of them, the famous Lost City, Rainbow Field, Broken Spur. They were hosted by different geologic patterns, but also they contain different fluid chemistry, which was more important for us because we were trying to understand, and we are still trying to understand with the samples that we are analyzing, which got interrupted, of course, because of the pandemic. We will continue when the labs will reopen. But anyhow, we were able to collect samples from different systems. One of our ideas was to understand, especially these nanoparticles, what controls the formation of these nanoparticles. For that purpose, we have also conducted a different type of sampling. In this case, we used an ROV, Victor of France, and we let the ROV actually stay at certain distances from the opening of the hydrothermal chimney. So 1 meter, 2 meters, up to 5, 6 meters, as much as we can, and then we try to obtain a gradient basically to understand how iron was transforming. So in this particular vent, we have samples from different vents, but in this particular example, you see the iron fractionation, size fractionation, and concentration data. So long story short, this is one of the evidences of, okay, we can image, collect, and take SEM or TEM images of nanoparticles, but you can also quantify them. Here we found that 5 meters above a chimney, this sort of nanoparticle iron was about 1 micromolar. In other words, it's 10,000 times more concentrated than the typical background, at least 10,000 times more. So it's a great source of very stable, kinetically stable iron to the surrounding deep ocean. These sort of high temperature vents are not the only iron source, however. So to illustrate that, I'll take you to another portion of the mid-ocean ridge. So previously with Serhat, we were in this area, northern mid-Atlantic ridge. And when you come to the Eastern Pacific here, you see a different system. And we were able to visit this system in 2017 with another IMS student, Dan Batuhan, who is now doing a PhD in Max Planck in Bremen in Germany. I think he's in the audience as well. Anyway, this system is different, hosts a quite different sort of biology, which I couldn't talk about much in this webinar. Maybe in later ones, I'll be able to share also those observations with you. But this particular vent field is very rich in what we call as diffuse flows. So diffuse flows are, they are not like these black smokers, which are 300 degrees, but they are milder, they are less hot, 30 degrees, 20 degrees. That's why you find animals here. You see typical tube worms chemosynthetic fauna around the East Pacific rise. Of course, then it became the hotspot of life with fish, crabs, mussels. So all this is based on chemical-based chemosynthesis. But for the purpose of our talk, we have also, now the water is a little bit less harsh in terms of temperature. We could also use chemical sensors to measure iron and sulfide. So we try to do this as much as possible instead of doing our sampling and onboard measurements. So long story short, what we found in this expedition, one of our findings was that these sort of low temperature emissions, they can contain a lot more iron actually compared to typical high temperature black smokers. So this is something not really well accounted for, but we believe that especially in off-axis areas, you find a lot of these sort of fluids seeping, later warm fluids seeping and entering and bringing iron and other things to the deep sea. So try to highlight a few things from our recent expeditions. When you think about these findings in the context of what my colleagues in the GeoTraces and relevant projects found is really very exciting, because some of these transects make it to the cover of Nature. Here you see this is the Pacific transect, iron coming out of the Pacific vents. This is the Mid-Atlantic. So now it's very well established that the iron coming from those diffuse flows or high temperature emissions, they can really be found thousands of kilometers away from their source. Of course, one of the ideas, in addition to particles, we should mention is the organic complexation. So the organic molecules can also bind and stabilize iron. And now the current thinking is that the long distance actual transport of iron is really a product of this joint collaboration between inorganic nanoparticle formation and their stimulation by nanoparticles. And now there's also evidence for the hydrothermal waters actually being upwelled, being advected lateral and upwelled, especially in the Southern Ocean. All right, I'll try to speed up a little bit. I'll come back to our questions again, and as I promised you, another important factor is sediments, of course. So when you consider the sediment input and the hydrothermal input, there are also superimposed processes of especially thinking about glacial cycles. This changes in sea level. Now we are finding that, as other people are finding, but we are realizing that the sea level putting in more pressure to the system can increase hydrothermal fluxes, which can actually help some of the iron fertilization that Martin hypothesized. So some of the increased productivity could be due to actually increased hydrothermal activity during the ice ages. Whether or not this is also can be applied for sediment flux is something to be seen. Again, back to these nice images, maybe you see also iron seeping out from the continental shelves, right? So basically these continental shelf sources, they don't just come out randomly. They come out, they exist. So iron is mobilized from continental shelves when especially you start to lose oxygen in the bottom waters, right? So I'm sure many of you are also aware of this problem of eutrophication and deoxygenation. So when this happens, especially in large areas in the eastern tropical Pacific and the Indian Ocean and the Black Sea, so huge amounts of metals can come from those seafloor if the OMZ, if the oxygen minimum zones intersect. So in IMS, we use, of course, we have excellent, one of the best model systems to study these sort of oxygen-dependent metal feedbacks. That's Black Sea, of course, well, thanks to our anthropogenic activities, Marmara is also becoming a relatively good system for that. Both systems are Black Sea is well anoxic deep layers, and Marmara is also becoming so each year. We now at IMS, we have a very extensive and transdisciplinary program addressing 2 seas. Here you see a photo from our expedition from last summer. We are looking forward to go back after all the pandemic issues are resolved. But long story short, we have also found evidence already of metal fluxes. That's some data collected by voltammetry in the Southwest Black Sea. And now we couldn't really study this problem in detail so far, but we will have a new project that will start one of these weeks. It will last 2 years to study metal mobilization in our seas, but with a view to understand this broader framework, basically how metals are mobilized from deep sea and how do they contribute to the long-term cycling, biogeochemical cycling, and the productivity of our planet. And as I also explained to you, when you go further back in time, the importance of metals become even more pressing. As I said, for many different metabolic functions, you have to have metals. Here you see the origin of different metabolisms, key metabolisms that life is based on, such as anoxygenic photosynthesis, metagenesis, nitrogen fixation. They probably all evolved in an anoxic ocean. This is basically before 2.5 billion years ago, when oxygen was not in the atmosphere. The oceans were anoxic. They contain a lot of metals such as iron, nickel, and cobalt. So all these metabolisms were able to evolve in a metal-rich ocean. But of course, now our oceans are oxic, not many metals. But in between, we had this time between 2.5 billion years ago and 0.5 billion years ago, where the ocean was partially oxic. The upper part was oxic, but the deeper layer were more sulfidic. Just as the present-day Black Sea. So in this Black Sea ocean, this is when you had phytoplankton evolved and diversified. And now we are also looking into how metal, especially availability in this type of Black Sea ocean, could influence phytoplankton evolution. All right, so I started out with plate tectonics, the revolution of plate tectonics, related to rise of oxygen and different metabolic innovations. But there's something we realize each day is how the evolution of the Earth's inorganic and non-living part is how it's tightly coupled to life itself. So here I would like to argue that we had the latest revolution in science, at least in physical sciences, was plate tectonics, and I'm very sure next one will be the oceans, how oceans control co-evolution of life and Earth's composition. And of course, this is going to affect our own future as well as humans. So with this, I would like to end, and I would like to thank to many people, collaborators, my mentors, George Luther, Nadine, different people who are, of course, with them we produced many of these ideas. I would like to also acknowledge my students. They are trying to attack this big problem from different. So if this big problem is like an elephant, we are trying to bite the elephant from different corners of it. I thank them for their dedication. We have a new website, thanks to them, where you can go and check out our recent papers. Of course, these ideas here you see that I tried to put together also is a product of different working groups, currently active groups, such as the SCOR working group 151, Iron Model Intercomparison. So, and another group is the Interreach Theoretical Institute. So these are photos from good old days when we were able to travel and talk to each other. Of course, lastly, I thank also my colleagues over IMS. Of course, we are being connected through Zoom regularly, but we are a very dynamic and experienced group here. So please consider us. For those of you seeking options, different options for graduate study, you can also check our website for more information, or you can contact us. Thank you very much. Of course, I have to acknowledge our funding sources. A lot of our research is really supported by the DECOSYN infrastructure project, which keeps our labs maintained, our instruments functional. So thanks to this infrastructure project, we are able to analyze many samples coming from all over the world and our seas. And the support from especially the Turkish Academy of Sciences and the Bilim Akademisi, the other science academy of Turkey, they gave maybe not financially big amounts, but they gave a morale, and it showed that we were in a good and right direction. So thank you very much. Now, if any questions accumulated in chat, I guess we can answer them. Or I think if you also need to comment something, I guess Barış Hoca, right? They can also.
Yes, and thank you, Mustafa, for this very interesting and inspiring lecture. And there are a few questions in chat. I will ask them to you, and we will limit this discussion session with 10 minutes now. And if people want to ask other questions or want to make comments, they're also very welcome to do so. They can raise their hands, and I will see that. Mustafa, there are two questions. Maybe you can quickly comment on them. First one is from Koray-san. He's asking about the effect of hydrothermal vents on climate change. If there's a positive or a negative feedback for the climate change, and also the feedback on the carbon storage.
Yeah, very good question, of course, from Koray. As I tried to explain here, well, where was that? Very good question, and actually we are doing a lot of literature search on this as well, and talking to people who are also thinking hard about this. And there are actually conflicting sort of results. When you look at, for example, hydrothermal deposits, when you analyze history of hydrothermal sedimentation, let's say, you can find in some places increased hydrothermalism in the ice ages, but sometimes you find less hydrothermal signature. But a recent paper by Lawrence Klugen shed a lot of light on this. So they presented some theoretical considerations of this. And apparently, the sea level is a big influence on this because it's pressure, and pressure is one of the major parameters defining the fluxes from hydrothermal systems. If it changes how much pressure you apply on a reaction system with magma and everything. And they found that increased sea level actually could lead to more and more fluxes. So in that regard, you could also argue that maybe not in the interglacials, but not in the glacials, but in the interglacials, you might have more and more influence of hydrothermalism on the global climate. But with regard to the feedback, it can be either way at this stage. To be honest, the evidence shows us that it can be either way. We don't know, and a lot depends on the type of the ridge. If it's a fast opening ridge, slow opening ridge, if it's a subduction zone. But we are looking into that. So I hope I can give you a better answer in a few more months. And the carbon storage, that's a very good question. It's almost certain that during glacials, more carbon was stored in the deep ocean. So to what extent this resulted from increased productivity, first of all, we need to think about that. And if this productivity resulted from the input from the deep, I think this could be possible. We know from other studies that during the glacials, the oxygen levels also dropped in the deep ocean. That might lead to more iron coming in from sediments too. Remember, sediments are also a big source. So I would say they have a direct influence with respect to carbon storage. It's a positive influence, I think. But climate change is difficult to tell which way it went. We need to look into that.
Okay, thank you. And the other question is, if this iron originated from hydroventral vents, if that reaches the euphotic zone and used by photosynthesis at that level.
Yes, thank you, Şükrü Hoca. Very good question, of course.
From Mustafa Mantıkçı, I'm sorry, I forgot to say.
Okay. Yeah, I also see from Şükrü Hoca coming up with a similar question. I think he wrote to me privately. Okay, yes, very good question by both. At the moment, of course, both sedimentary iron sources and hydrothermal sources can come or arrive to euphotic zone via upwelling. The question is, how would you produce upwelling? Of course, there are more experts than me on this idea, but at least we know now that mesoscale processes can cause these sort of upwelling. Internal waves can mix up some benthic environment and yield to some sort of vertical transport of, again, any deep sea product to the surface. This is happening over continental shelves. But on a global scale, more ocean scale, this lateral advection seems like a very, very big possibility now, especially in the Southern Ocean, because this is how, as you know, Southern Ocean is a very mixed up place, cold, and it's very related to the deep Atlantic. It's directly linked. So any vent product entering the deep Atlantic, and if it's stable enough, of course, if it's chemically stable, which we show that it's possible, then it's apparently, from what my colleagues tell me and from these papers, apparently physically it's possible to laterally transport and advect this vent or these deep sea products to the euphotic zone, at least in the Southern Ocean. And as you know, once you change the Southern Ocean biogeochemistry, you may change the climate. So these are the processes at local scale, upwelling and mesoscale processes, but in the large ocean scale, it's the lateral advection and upwelling.
Okay, thanks a lot. And there is a question from Batuhan Çağrı, and he's asking about the possible relations between metals from hyperventral vents and polymetallic nodules on abyssal plains. And he says, of course, the distance between sites is high when you consider oxidation rate. Do you think is there a way to trace those metals to reveal a possible relationship?
Yes, Batu, that's a first of all, that's a very good question. Normally we think that, well, the polymetallic nodules, just to briefly talk about them, they exist really deep, 4,000 or 5,000 meters, maybe 6,000 meters deep in really abyssal plains far away from mid-ocean regions. At least this is where we found them lately. Of course, we need to look at where these polymetallic nodules are found, if they are along a axis of hydrothermal plume. But the difficulty with this is that we have only 1 or 2 hydrothermal plumes mapped at the moment. I mean, the papers you see by Jessica here, Jessica Fitzsimmons, and some other, these sort of data are just coming in. And I know from my physical oceanography colleagues that it's very hard to simulate, because lack of data, these sort of hydrothermal plumes in big physical models. So we need to look at, maybe we need more data from deep sea. We need to look at if these nodules that are concentrated in certain places, if they are like along a path of hydrothermal plume. But if it's so, it's very possible that this can be a flux of metals. But in the end, you know, Batuhan, as we've also discussed in our course during your masters, the source of metals for the polymetallic nodule comes from sediments. So, but the hydrothermal plume can bring some metals to the sediment itself. Then, of course, a few million later, that metal can be rediffused back to the seafloor to make the nodule. So, I think over longer time scale, if you increase your time scale to millions of years, yes, there will be a connection, I think.
And thank you, Mustafa. And I would like to thank everyone for joining this seminar. And if you have any feedbacks about our webinar series, please feel free to contact me. And please follow our Twitter, Facebook account, and also our webpage for the announcement of the next webinars. And I would like to wish everyone a good weekend. We will be in lockdown for the next 4 days here in Turkey. I hope you all stay healthy and safe. and hope to meet you again in 15 days. And thank you, Mustafa, very much again for this very interesting seminar. And thank you everyone for joining and also for the great discussions. Okay, bye-bye. Take care.